Okay. So today we'll discuss cache coherence. And if you see, if I go to first slide, this you can see this slide is for advanced level course. This is for elective course. But the same slide I'll use here because the concept of cache coherence is very important. Even if it is a core course or it's a advanced level course, this topic is very important. Why? Because even today, if you sit for any job interviews or for any computer architecture related companies, then this is one of the most important topic from where they will ask question to you. This is one topic. Another topic is called branch prediction that we will discuss maybe after 1 or 2 weeks. Pipelining, cache coherence, and branch prediction. These are the three topics mainly the companies like Intel, AMD, Qualcomm, uh, uh, this type of all other architecture related companies will ask. And uh, uh, why I'm saying this because nowadays these architecture related companies they want more people because nowadays maximum people are shifting towards some other areas, right? So now there is a vacancy in these areas also. So and it will be there for few more years. So make sure that when we will sit for you'll be ready for placement at that time. You should know the this concepts also because at that time these companies will be also available for it. Though these companies also require basic concepts like right, but this basic programming and all concept those concepts are common. But excluding those concepts also, if someone knows the concept of cache coherence, branch prediction, pipelining, then it's an advantage. And it's not the end here. If you are selected for a companies like this, and if you are the maximum time your work will be based on either cache coherence, branch prediction, or something. So if you don't know the basic concept of cache coherence, then it will be very difficult to do any work in a multi-core setup. Even the simulation that I have given you, simulation to GemSim is a very simple simulator. So many things are as means abstracted out here. But if you go for a real full system simulator like Gem 5, so here if you want to do a small change, then also you must aware that how the underlying cache coherence will behave. Otherwise you cannot design, there will be some issues. So first thing I need to explain here is what is cache coherence and why it is required. So some basic example will be, suppose there is a block here A in L1 and this block is also here in L2, and after some time if this core C2 is requesting for the same block, and now there will be a miss here in this L1, so this will go to L2 to fetch the block, and now there is a hit in L2, right? So if L2 sends the block to this L1, suppose everything is nice, but what about if the copy that is here, this copy is updated? Maybe when core 1 requested for this block A, after requesting this block, core 1 has updated, core 1 has written something to it. So if the initial value of A is 10, now the core 1 has updated it to 20, suppose. So if in that case, if core 2 is requesting for A and the last level case is supplying the copy, then it will get the old value. So it means that we have to do something such that both should get the new value. So there should be some protocol here. There should be some protocol here. So that protocol is called cache coherence protocol. So since there are the coherence protocol is not required if you have a single core processor, but single core processor is not a recent design, right? In modern design, any processor is a multi-core processor. So in multi-core processors, we should need a mechanism to handle these type of scenarios. So this is just an example I have given you to understand what is called coherence. So there should be some rules. Based on those rules, you should update. You cannot, if a core is requesting for a block, it's not like that immediately it will get that block. Because so far what I have explained in class, that if there is a miss in L1, we'll go to L2. If there is a miss in L2, we'll go to main memory, and then we'll fetch it first to L2, and then we'll store it in L2, and then a copy will be sent to L1, right? And once a copy is there in L1, then from the complete block, one word will be sent to the core. That part is done. But I have never explained that that this is not every time it is not possible. Sometimes before doing these activities in the middle, you may need to follow some other rules. That is called coherence protocol. So to understand, so this lecture will be continued. I think today I'll after this lecture, then the next lecture will not be on cache coherence. Next lecture will be taken by my PhD student on replacement policy. So you'll get some time. So try to understand whatever I'm explaining today. Okay. And then in next class, when I'll continue cache coherence, then if you have any doubt, that time you can ask me. Today also you can ask, but if you after today's class also, if you face any doubt, then you just note it down, and the next class when I'll continue cache coherence, then you can ask it to me. So before starting cache coherence, there are some important terms that you need to understand. But I think all of this term I think already introduced in class. What is cache block? You know what is cache block. Private cache, shared cache is also explained. I think if you see the diagram here, then there are two cores in this processor, C1 and C2. So both the core has their own private L1 cache. Normally L1 cache is divided into I cache and D cache, right? Instruction and data. So I'm not showing it here. Just assume it that they are divided into two parts. And both the core are sharing a L2 cache here. So L2 cache is there is shared cache, but L1 are the private. L1 is a private cache for both the core. Okay, then there are two concepts called multi-programmed and multi-threaded application. I think I also introduced this term, but let me explain it again here. Multi-programmed application means if there are two cores, so if you run two independent application on these two core. Suppose in core one you have two programs. Suppose C1 P1.c and P2.c. You have compiled these two programs, and now you are running one program in core one, another program in core two. Then this is called multi-programmed application. And if you think about real life, then maybe in one core, if you are running MP3 song, another core you are running some editing software, then also they are independent applications, right? So this is called multi-programmed application. Multi-threaded application means same program, but there are multiple threads. So operating system is already introduced in your syllabus or not? Okay. So when you study operating system, you will know two concepts. It's called process and one is called thread. So process means if I said every time if you are creating a program, suppose a.out is a program, right? So that the moment you start run this program, a process will be created, and a process has its own memory. This is the memory of a process. Suppose. So if you create one more process, then there will be a separate memory for this. Okay, but if it is a thread, then there will be one program only, but within that program, there will be multiple threads. So all the threads share a common space. So if there will be multiple threads within the process also, that there can be multiple thread, T1, T2, T3. There can be multiple threads. So threads share the common address space. So I'm not going in detail about address space because I have skipped the virtual memory part. So when I'll explain virtual memory part, then at that time I'll again explain. Or if you want more, maybe I'll share one recorded video, but again, that will not be in your syllabus, where I have explained this concept of process and thread in more detail. So you can check that video I'll share. But in short, every time if you run a program, then when you run a program, a process will be operating system will create a process for you. In that process, your instructions of the program will be there. Then a space will be there for storing your dynamic memory allocated memory, that is called heap. Then there will be a memory there called stack, where you store all your local variables that you declare. So there will be a separate process. So if there are multi-program applications, so there will be two separate address space for them. Okay, so suppose if I say about multi-program, then suppose there is a block here called A and there is a block here called B. Okay, so if program 1 is running here and program 2 is running here, so the last level cache is shared. So B can also store here and A can also store here, right? This is that's why it is shared. Though there are two process P1 and P2 running and they have two separate address space, but both the process can use L2 as a storage. Okay, they can L2 as a storage. So this is called shared L2. Now another thing in thread, if I remove process, then thread has a common address space. Right, multiple threads are there, as I said, T1, T2, T3. So all the threads here have the common address space. So in that case, what will happen? Suppose there is a block called A here, and now remove this P1, P2. Suppose there is one thread here and one thread here. So now thread 1 can also request for A and thread 2 can also request for A. Same block. So suppose there is a block here A, the same block can be requested by T1 also and same block can be requested by T2 also. It may be possible because their address space is same. There are just multiple threads within the program. So in that case, suppose T1 is also requested for A and T2 is also requested for A. This situation may be there. In that case, in last level cache, we normally store a directory one, suppose 1 comma 2. 1 comma 2 means in last level case, it's stored that which are the code which is currently sharing this variable A. So that is called sharer information. So we store sharer information in this way. Okay, so one more advantage of writing a thread is, since the thread is not introduced in the in your course yet, you suppose there is a program for matrix addition or array addition. Suppose there is a long array. There are two long arrays are there, very long arrays, and you want to add them and store it in a final result. So third array is your result. You can easily write a C program for this, right? There are two arrays. You need to just run a for loop, and then one by one you can store in the third array. But assume that, as I said, the array is array is very long, and maybe the size is there are millions of entries are there. Okay, maybe there are 1 million entries are there. So if I run, if you, because there will be 10-15 line C program, very easy. If I run that C program in this laptop, and suppose it is taking 5 seconds to complete it, so this we are not utilizing the laptop properly, because this laptop has 4 cores, and if you write your program, it will run in only single core, isn't it? So in single core it will run, but if somehow we can introduce thread there, and you can say, no, I can, since this computer has 4 core, let us create 4 threads. So what I'll do, I'll divide this problem into 4 parts. So thread 1 will compute this part, thread 2 will compute this part, thread 3 will this, and thread 4 will this. So what will happen, that this complete task will be distributed, and in all the 4 core, this same task will be performed in parallel. So if previous it is taking 4 seconds, maybe now it will complete in 1.5 seconds. So that's the beauty of a multi-core system. Otherwise, if you see, I hope you know now frequency now. So nowadays, if you see the Intel i7 processor, frequency is still, I think, 2 point something, 2.7. That frequency was there in 1999 also. When Pentium 4 was there, frequency 2.5 was there. So why, if frequency has not increased, then how performance is increased? There are a lot of other things also, but one point is, now with low power, same frequency, but we have 8 cores, isn't it? So at the same time, we do simultaneously different works. So okay, one thing is, you can run multiple programs in your computer, multi-program, that is fine. But in a single program also, if you have the thread concepts, then you can run it better. So that's why there are 2 points. One point is, no matter how good your computer is, it is still, there is some responsibilities there on software engineer also, that they should also know the underlying architecture. If their program has no support of threading, then ultimately this computer cannot do anything, right? So there are some tools which which can convert your or sequential program to a multi-threaded program, but anyway, those will be done by programmer only, right? Those are also human beings. So maybe you may design this type of tool also, but ultimately, if you have just a single sequential program, then it will not give you improvement. So that is the concept of thread here, and this point is very important, that if you have a very high configured computer, then it may not improve the performance. Ultimately, performance improvement is also a responsibility of software engineer. The software engineer should know that how a architecture is behaving. Okay, so if multi-program and multi-thread applications are clear, replacement policy is also clear to you. You know what is called replacement policy. Cache structure is also clear. At this moment, if you only know the behavior of a set associative cache, then it is enough. You know how set associative cache behaves. Okay, some more important assumptions I will take here. The cache structure is set associative only. There are two other designs also there, right? Direct and fully associative. I'm not considering it here. The replacement policy that I'm considering here is only LRU to make it simple to understand. There are two cores only, C1 and C2. Each core has their private L1 cache. You can see from the diagram. Both cores share a common L2 cache. That also you can see from the diagram. And both core run multi-threaded application. I'm assuming multi-threaded means they can share one common block also. It may be possible that there is a block called A, which is requesting by both the cores. It is possible here. More assumption. Let us assume that all the set associative cache in this diagram is only one set. Well, I'm assuming only one set because it is easy to understand everything. So assume that it is a set associative cache, but there is only one set. Or you can say there are many other sets, but I'm whatever blocks will take are mapping to the same set. Okay, and with this, I think these are not important for you. I think I have introduced NUCA in class, right? S NUCA, D NUCA, TCMP because so even if you are not understanding this concept, then also it is fine. ये remove नहीं हो रहा है anyway. रहने दो. CMP is important. I think CMP मैंने introduce किया है class में. CMP means chip multiprocessors. So whatever multiple processor available in the market, they are actually CMP. CMP means within a single chip or single die, multiple cores are there. So you can see this you can consider as a CMP. So if it is a CMP, then there are two cores here, L1, L2 case. Everything will be a single die. So that is called CMP, chip multiprocessors. Okay, so with all these assumptions, I will go to the next slide. Cache coherence. So there are different cache coherence protocol exist. So we will only discuss protocol here first. Okay, before going to cache coherence protocol, one more thing, one more point is required. If, so far we have said that if core requests for a block, it will go to L1, will search it L1. If it is not in L1, then it will go to L2. So there are some logic here, right? If it is not in L1, will go to L2. Who handle those logics? Isn't it? I have never explained this. If it is not in L2, then we'll go to main memory. I have also explained that if you are removing something from L1 and if that block is dirty, then you have to write it back. But who is doing this? Because those are conditions, right? And someone should do this. So that is performed by a this. You assume that's the block, the circle that I'm designing here. This is called cache controller. So this is the responsibility of cache controller. So every cache has a controller. So here there are three cache memories. So there will be three controllers. So basically, when C1 will request for a block, when I say the core is requesting for a block, actually first it is requesting the controller that I want this block, and rest is the duty of controller to provide that block to the core. So if there is if core will request for a block, first it will reach here in controller. If then controller will search in this L1. If the block is not in L1, then the request will send to L2. Actually, it will send to the controller of this L2. Okay, and then next is the responsibility of controller how to send the block to the upper L1 cache. Okay, so but from the next slide, I'll not mention this controller. I'll just say that L1 is sending to L2. You have to understand that there is a controller which is handling this. Okay, so now the coherence protocol that I will explain here is called MSI. So MSI means M means modified, S means shared, and I means invalid. So these are the four state of a cache block. So every block that we fetch from the memory and we store in the cache. So if we follow MSI protocol, then there will be three possible states for them. I state of a block means any block. If I store here a block called A, you have to assign a state with it. See, if I assign a state called I, it means invalid, means not present. The block is not in the cache. When a block is not in the cache, we say that the status of the state of this block is I, invalid. Sometimes we also call it NP, not present. Both the same. If I say that the state is S, that means it is just in shared state. Means it is in read-only mode. Means all the core can read it. If there are two requests from two core, then both core can read it. It's in read-only mode. If the state is M here, It means it's a modified state. Modified state means if it is in modified state, then it means that either core 1 or core 2 has exclusive permission on it. Means maybe if I assume that modified state is like this, so it means that C1 can write on this block now. So at this moment, core 2 cannot access it. I'll explain it in more detail. So better if I write modified and share here, then it is good. If I write s here, then means core 1 can only read this block because the permission mode is shared. Okay, so if I write m here, then it means core 1 can write also in this block because the state is now m. So m, s, and I, there are three states. And now there are some events I'll introduce: event, get s, get x, all the events one by one I'll explain. So what I'll discuss, as I said, that there are controllers for L1 also and L2 also. So whatever concept that I'll discuss now, it's actually the content of L2 controller. This controller I'll discuss. I'll not discuss L1 now. I'll just explain that what are the rules required when you send a request to L1, L2. So when L1 will send a request to L2, how L2 will manage? What are the rules for L2? What are the protocol rules for L2? That I will explain. And after that, I'll quickly explain L1, because once you understand the concept of L2, then it will be easy to understand the concept of L1. So get S request. If you remember, if I write a statement like load, suppose x1 24x2, then this is a load instruction, right? So load instruction, when it will go to memory, assume I'm not going for instruction fetch part. In instruction fetch, all the instruction is going to cache to read it. But in case of data, the load instruction will go to cache memory to load something, right? So it will go for reading something. So load instruction means code will request for a get x request. Get s means get the block in shared mode. Okay, so for every road instruction, core is requesting only for reading, right? So that request will call as get s. If there is a store request, then we want to write something to that memory address, right? This is a memory address, this is the memory address, and we want to write something to this memory address. Writing something means core should request in get x. Get x means it should request for exclusive permission. Exclusive permission, these two are very important. So what I said here, that if core is requesting for first time, suppose here the block is called a, so core will request for a block a here. Again, I am not ignoring the term called what, I'm just explaining everything in terms of block. So there will be a get s request here for a, and if there is a miss here for a, then now request will be forwarded here in L2. So now we are only saying about this request. So this request will be again a get s request. Get s request, right? So get x means if core is requesting for a block to write something, and if it is a miss in L1, then this again the same get x request will be forwarded to L2. So how L2 should handle it? So that is called get x. Now upgrade. Upgrade is interesting. Upgrade means if suppose core 1 has first requested a block a in shared mode, and we have provided the block in shared mode to core 1. This is the current situation at this moment. So initially, suppose the same example, if I give, suppose x1 24x2, this was the first line. Assume this block is a. To execute this line, core will request for a, and the request will go to L2. Ultimately the data will come from main memory and then L1. Now this is the situation. Now the after, maybe there are some instructions here, and then there is a state instruction here, same address, same effective address, it is also for a. So now core 1 wants to write something to same block, and do you think it is possible now? Because if it is sending a write request now, at present in L1 of core 1, the block is present in share mode, so it cannot directly write. So it means that is it in, if this is the situation that okay, core 1 wants to write something, means core 1 is requesting for some get x, but permission is not here, though block is here, there is a hit here, but even after hit you cannot write it there because it is only in shared mode. So in this case, this block, this L1 will send an upgrade request to this L2, that oh, I want to upgrade my permission. And why it is sending to L2? Because L2 is shared here, right? So L2 is behaving as a directory. So I'll discuss this part later. So let us just assume that there will be upgrade request will come to L2. Upgrade means that this core has this block, but now currently in S state, but it want to upgrade from S to M state. So this is called upgrade. Now putex means suppose, as I said, I'm only considering one set. Suppose A, B, C, D. The set is full. Four-way associative set is full. Now, if core is requesting for another block, suppose block is called F, then we need to remove something from this set, right? From this L1 to place F. Suppose this one is the victim. We want to remove A because assume A is the LRU block. So if A is not dirty, then very simple. We can remove it directly, no problem. But if A is dirty, then we have to write it back, right? So that is called putex. So if A is that dirty, then we have to write it here back. Otherwise, the updated value will be lost. So that is called your putex. Okay, and since as I said that whatever events I am writing here are for L2 only. So suppose if your L2 is also full, suppose then there are many other blocks. L2 is also full. If L2 is also full, and if you want to fetch a new block and place it in L2, then you must remove something from L2 also, right? So if you want to remove L2, then you need to replace something. Suppose you have this is the victim, A is the victim. Suppose, can you remove, assume that A is not dirty also, can you remove it directly in L2? Whatever the current situation, can you remove it directly? If it is an inclusive cache, I have explained once inclusive and exclusive cache, right? If it is inclusive cache, you cannot silently remove, because if you remove it from L2, there is a copy of this is there in L1, right? So that is not satisfying the inclusive property. Inclusive property means whatever they are in L1, a copy must be there in L2. Maybe that copy is old, but the copy will be there. That is called inclusive. So if I assume here inclusive cache, then you cannot silently remove A. Agar आपने remove किया, so inclusive property will not be managed. So what to do? Before replacing this A from L2, you have to send a message to this L1 that, see, I have to remove this block from my cache. So you have to invalidate your copy. So first L1 will invalidate this copy, make it I, and then send an acknowledgement that, okay, I have done it. After getting this acknowledgement, only the block can be removed. So there is a long process here, right? This process will be handled by this event, replace. Okay. And there are two replace here, replace and replace clean. I'll discuss this later. Replace clean mean if this A here is dirty, then even after invalidation also you have to write it back. And if A is not dirty, then you can simply write it. So there are two replace and replace and replace clean. There are two concepts. So now one by one we'll try to understand all this. So these points are clear. Cache block status, state, M, S, and I is clear. Hello. And events, get S, get X, upgrade, put X, replace clean is clear, right? Inclusive and exclusive cache setup is also clear. Now one by one we'll discuss that. If here I'll write suppose this is C1 and this is C2. If C1 is requesting for a block A in S mode, means get S mode. Okay, if C1 is requesting for a block A in get S mode, assume that there will be miss in L1, because I'm only considering this request. I'm not considering this request. Okay, so C1 is requesting for AS. So A in get X mode. So what is the current status here in L2? A is there in L2? No, right? So you can say current state of this block A is I. Current state is I. So if current state is I in L2, only concentrate on L2. If current state is I and you are getting a GETS request, you means as a L2 cache. So you are getting a GETS request, then what to do? This is the first point here. If current state is I and the L2 cache is getting a GETS request, then what to do? We all know, right? If it is a miss, we'll go to main memory, fetch the block and store it here first as A here, and we'll store it as share state A, and then we'll send a copy back to this L1, right? We'll do this. So this is what we need to perform. So it means that if the current state is I and you are getting a getters request, then next state of this block will be S, right? And before that, you need to do some actions here. What are these actions? These actions are going to main memory, fetching the block, sending it to upper level. All these things are, I'm not discussing, just I'm saying this is the set of actions you need to do. So FSM is known, this course, automata course is already introduced in your syllabus? No. So do you know what is called FSM? Yeah, so I'm designing FSM here. I think in from digital logic course, you know the concept of FSM, right? Okay, so this is done. So now after some time, suppose if code 2 is requesting for a block B in exclusive mode, I'm writing X here, that code 2 is requesting for a block in exclusive mode. So it means that B is there in cache? No. So current state is again I, right? So in I state, if you are getting a getX request, then what to do? Again, simple. I'll go to main memory, fetch the block here, store it here, and states will be M. And then I'll provide B here, and state will be M. So it means that from I state, if I get a get X request, then next state will be M, and I'll do some actions here. I'm not writing those actions. So see, one by one, I'm building this FSM. So every time if you see a book of in any book or any website, if you want to understand cache coherence, you'll see this type of FSM. So initially, it will be difficult to understand what is written in FSM. But if you understand, if you know how to understand the basic concept, then you'll understand it. Okay. So now these possibilities are not real. Means other means except getx and maybe I'll let me write all these things here. Chala gaya hai. Get s, get x, then upgrade, put x, and replace नहीं लिखते अभी, replace बाद में होगा. So do you think upgrade and put x possible if current state is I? Upgrade कब आता है? L1 से. If L1 has a copy in S mode and then L1 is requesting to upgrade. अगर and if the cache is inclusive, so if the block is not present in L2, there is no chance that this block is present in L1. So if the current state of this block is I in L2, so upgrade आने का कोई chance नहीं है. Okay, the same is true for putx. If the block is not in L2, then no chance that it will be in L1. और L1 में यही नहीं तो कहाँ से putx आएगा, isn't it? So that's why I'm making I have this are not possible at all. So now go to S here. Now if code 2 here is requesting for S a block A, so code request will come here in L2. It will be hit or miss. It will be a hit, right? So if it is hit, means what is the current state of this block in L2? S. So current state is S and a getters request arrives. So how to handle it? Obviously, you will not go to main memory. Block is there. And if it is in shared state. So since it is in shared state, there is no problem. A copy of this block will be supplied here. And here we'll mark 1, 2. Previously, here also we'll mark 2 that I forgot. This is called share information. That how many code are currently sharing it. It may be possible that there are 16, 17 codes are there. So which are the codes which is currently sharing? So this information is called sharer information. So you can see there are two metadata I have introduced today. One is state, another is sharer information. Tag, dirty bit, valid bit, all are I have already introduced, right? At that time I said that you will see more metadata. You can see there are two more metadata. One is called state, another is called sharer information. Normally sharer information don't store in this way 1, 2. They normally store a bit vector. I hope you know bit vector means only 2 bits will be enough. Here I'll write 1, 1. 1, 1 means it is present in both the core. If there are two cores only. If I write 0, 0, then it is not present in both the core. So normally they use bit vector, but to understand it better, I've just written 1, 2. Okay, so get s is done. Now, if okay, इसके बाद s get x है ना, s get x को एक्सप्लेन करने के लिए क्या करना है, थोड़ा मैं चेंज कर लेता हूँ इसको. इसको s कर देता हूँ. Whatever I've explained previously, assume that it's a new scenario. It's a new scenario. Previous explanation was all correct. Don't think that I'm correcting B. It means that previous explanation was wrong. I'm just recreating another scene. So it's a new status of this cache. Suppose this is the current status of this cache, and in this time, core 1 is requesting for B in exclusive mode. First, try to understand the current scene here. So both the block A and B are in shared mode, right? And both the core are currently sharing them. Now, obviously, I think in this case, L1 से तो getx नहीं आएगा, right? If now L1 wants to access this B in exclusive mode, then what L1 will send? It will send upgrade, right? Upgrade send होगा ना? So what I want, because see, B भी यहाँ पे था, 1,2 लिखा है ना? So this is the current state. So in this state, if C1 wants B in exclusive mode, so upgrade आएगा. So I want to show you I want to show this. So उसके लिए मैं क्या करता हूँ, एक और core introduce कर देता हूँ. Okay, there is one more core. Now this core C3, ये नहीं, ये already हो गया है suppose. Now this core C3 want this block BX in exclusive mode. Now it is clear. Two core is there already, and now third core C3 is requesting B in exclusive mode. So current state of B, what is the current state of B in L2? S, and a request is you are getting for getx, right? So this is the combination. This is the combination. So how to handle it? The block B is already in L, right? Already in L2. So do you think I can directly send a copy of B here for this C2? I cannot send. So what I need to do here? Before sending this block to B, what I need to do? I can see here from this block that it is sharing by core 1 and core 2, right? And one now core 3 is asking it for exclusive mode. So first I will send two invalidation requests here and here to these two cache. Let's see the block that you are holding in share mode now. Someone else want to write something on it. So you have to invalidate your copy, otherwise your copy will be stale copy. So after getting this invalidation request, both this L1 cache will invalidate their copy. So I'm just making cross here. So invalidate their copy, and then both will send an acknowledgement to this L2. Let's see, I have invalidated. So when this L2 will receive acknowledgement from both the L1, then only this will be changed to M. Now this B will be M. Let me remove everything, otherwise it is. So after this, the block B will become M, and we'll write here 3, and now we'll send it here in exclusive mode. So you can see there are a lot of activities going on, right? So I think I missed something from here. If from S you are getting get S, then there will be a loop here. Nothing will change. If it is for get S में है S request आ रहा है तो get S में ही रहेगा. You'll do some actions also, but if it is in S state and you are getting a getx request, then it will go here. Obviously you'll do some actions here. So that's why whatever I'm saying, it's a rule, right? Whatever I'm saying, each and every point is a rule. So that is called protocol. Whatever I'm saying, point 1, point 2, it will send invalidation request, then it will wait for acknowledgement. After getting acknowledgement, it will send the block. So all this point that I'm saying, step 1, step 2, step 3, these are some rules, and that is called coherence protocol. What I'm discussing here, this is the coherence protocol. And who is maintaining this? The controller. The FSM that I'm designing here, this is a logic, right? Every FSM is a logic. So the same logic is implemented in your controller. If I say that this is the cache controller, then whatever I'm explaining here, you have to understand that this is the logic of this controller, and controller handles this. Okay, so I'll remove C3 now. C3, or I'll not introduce C3 here. Let me clear everything. And maybe I'll go for a fresh example. Now the next is S and upgrade. Upgrade के लिए तो suppose AS is here, AS is here. Okay. Now if core is requesting for upgrade, or suppose let make it more complicated, 1,2. So इसने भी A के request किया. Now if A is requesting for X, ये हो सकता है, right? So in this case, when core will request for a X, so A in L1 here, the block is already there. So it is a hit, but it cannot write because it is share mode. So it will send an upgrade request. So in L2, the current state is S and upgrade request is coming. So this is the situation. So from S, if there is an upgrade, तो कहाँ जाएंगे? So again, I cannot, L2 cannot send directly the M permission, right? Before that, now it will send a invalidation request, but not to both, right? It will only send invalidation to this two. It will send here and say you have to invalidate this copy because core one now want to upgrade in shared mode. So once it will receive the acknowledgement from here, then only this A will become updated here to M. And now I'll only write here M. Here one, you can say it is not the sharer information, it's the owner information. Now this block is exclusively owned by this L1. Okay, and यहाँ पे ये I हो जाएगा, or maybe you can say invalid means delete हो गया यहाँ से. So it means that if there is a upgrade request also and the current state is S, then also you'll go to M state. Maybe the action will be different, little bit different, but you'll go to M state. Upgrade ho gaya. Then after upgrade, this is next is putex. Putex is simple. Suppose A, B, C, D, as I said. This is full, and suppose the block A is also here. Obviously, अगर putex आ रहा है तो इसका मतलब यहाँ पे भी A M है. I'm not writing everything here, and here also it is M, right? Now only L1 can send a putex request. Means when putex request will come, that if the block is dirty in L1 and I want to remove this block from L1, right? So dirty कब होगा जब आपका पास M permission नहीं होगा, you cannot write something on it, right? So it means that suppose the block is, if it is in M state only, then only you can write it here. So when the putex request will come, obviously the state of here will be in L2 only. So if a putex request is coming, so it will be here, it will be, there will be a loop only here. So state will be remain same, or maybe we can say that state is changed from, yes, I think if there is a putex request coming, so it means block will be removed from here, right? So block यहाँ से remove हो जाएगा. So what we can do, we'll write this updated copy here. Suppose this copy A is old now. So suppose I'll update it now. This is the updated copy of A. अभी उसको M रखने का कोई मतलब नहीं है, right? Because it is already removed from the L1. So let us make it S. So you can say in that case that loop नहीं होगा यहाँ पे. From M state, if there is a putex request, then we will put it in S state. But you have to remember one thing. This A that I'm saying here, this A is dirty. Dirty bit आपको on रखना है, isn't it? Because L1 has written something to this A, right? And now updated copy is in L2. पहले वो L1 में था, now updated copy is in L2. So the block that is here A in L2, it is now dirty after this putex. So that dirty block has to be set. कौन set करेगा? According to this rule. जो actions यहाँ पे होगा ना, in that action, one of the action will be put this as a dirty block. So वो dirty होना चाहिए ताकि next time when you will want to replace from L2, then you have to understand this is dirty block. I have to write it back. So as putex हो गया, now the scene is different. Sorry, AM. अभी सीन ये है कि A is first requested for getX. Now here is requesting for S mode. Now core is requesting A for S mode. Okay. So now request will reach in L2. Current state of L2 is M, and request is getS. Means this core is requesting for A now in shared mode. So can we directly give it to L2? No, because as I said, M means exclusive state. It's not like there's किसी के पास S है और मेरे पास M is not possible. Since now the moment this request will reach here, this L2 is we are assuming as a directory. Why we are assuming? Normally, if you read the same concept from a book, then normally they will not say it L2. They will assume that L2 is a different cache, and whatever information I am saying, they will store it in a different, means state, sharer weight, they are storing you may store it in a different module that is called directory. यहाँ पे directory को मैंने L2 के साथ merge किया है to make it easy to understand. Okay, so when the request will come here, so we'll understand that okay, it is in M state. किसके पास है वो भी लिखा हुआ है यहाँ पे 1. So I cannot send it first. Again, I'll send a invalidation message here, and then this copy will be invalid. और उसको देना, but this is also not correct, right? Invalid क्यों करना है? Because this person is requesting in S mode. So best option है कि इसको भी S करो, and then इसको भी S, make it 1,2, and इसको भी AS दे दो. They have to do this. So इसका मतलब है you cannot send invalidation request. Because if you send invalidation request means you are giving a command, right? Invalid command means invalid karna hai. So you have to give something else here. So here normally we give a command called a different command like data forwarding. I forgot the command, but it should not be invalid. It should be a different command. And based on this command, what it will do, I'll again explain it to you what it will do. There is some more task here क्योंकि ये थोड़ा complicated scene है. Okay, so normally a request will go here called forward. Forward means L2 will say this L1 says see, because we can assume that this is the updated copy, right? We don't know, maybe this block is dirty. L1 ने M state में लिया, maybe उसने write भी किया. So updated copy is in the L1. So this L2 will send a request to this L1. It's called forward request. So see, copy of this block. You have the exclusive permission. Now another core is requesting for this block. You share a copy with him. So what this L1 will do? This L1 will share the updated copy with this. Now a copy will be here, and the state of both and both it will be S. Okay, this L1, first L1, left side L1 will share the updated copy with the right side L1. Okay, and now both state is S. But sir, one more point is there. This sharing and this state जो SS हो गया है, अभी तो वो L2 में reflect नहीं हुआ. So this updated copy, one copy must be transferred here also ताकि ये भी S रहे. Why? Because क्या पता एक और core request करे. Isn't it? So there are a lot of activities here. So if you go for M get S, this is called forwarding. This is called you from one L1 to another L1, and at the same time you have to update the same thing in L2 also. Is a point that I'm saying update the same thing in L2. That will be not required if you go for some modern coherence protocol, because MSI is a very basic protocol. It is easy protocol to understand in class, but no processor use it. So next is called messy protocol that I'll explain in अगर मेसी होगा तो आफ्टर फॉरवर्डिंग यू इट इज मेसी में भी चाहिए जो आई थिंक नेक्स्ट इज मोएसी MOESI. अभी समझ में नहीं आएगा तो कोई प्रॉब्लम नहीं. So if the instead of messy protocol, agar if you are using moesi protocol, then this write back, that is you after sharing forwarding here, L2 may not be updated. So one updation you can save here, because here what we are saying in MSI protocol, then first this left side L1 will share it with right side L1, and the same copy will also need to be updated in L2. The last updation, there is L2 updation, it will be not required if the protocol is moesi, not messy. So in modern processor, I think if I consider the processor of this laptop, they use moesi. Intel i7, I think they use moesi protocol. So this is just a beginning. If I then if you want to understand every coherence protocol, I think one complete semester will be required. But you have to understand gradually. You have to, because I'll explain MSI and MESI protocol. Both I'll explain, but other protocol I'll not explain. It's not required for this course, but it is very important. You should whenever you'll get time, try to understand what is the difference between MESI, what is the extra thing is there in MOESI. And I think after MOESI also there is MOESI if protocol is there. There are different coherence protocol exist. Okay, I think after this, the next is easy. I think if you have a M state and another person is one it's in M state, then it is easy, right? A M hai yahan pe A M hai, it is in 1. Now if C2 is requesting for same block, C2 is requesting for A in X mode. So ये state आ रहा है. Current state आपका M है, but you are getting a getX request. So in that case, also also you need to first invalidate this one, right? Here forwarding is not important because other person also want to write something on it. So update के ऊपर write करेंगे, पुराने के ऊपर write, it's not very important, right? Ultimately, important thing is the last write. So last write to C2 ही करने वाला है, right? So this updated value that is currently in L1, it's not very important at this time. So either you can forward it or you can invalidate it also. So I am assuming that I will first send a request here to invalidate it. So ये block invalid हो गया, then I'll get an acknowledgement here that it is invalidated. Now I'll give AM here, and this bit will change from 1 to 2. You can do this. It's not because the other person is also getting want it in getX mode. Okay. And M state में है upgrade. ये आ सकता है क्या? Is it possible? What do you think? That suppose there is a block here in M state, and suppose it is in M state here, current state is 1. Do you think a upgrade request can come in L2 for this? Upgrade request, when we generate upgrade request, if it is in S state, right, and wants to write something. So I don't think it can, because अगर किसी के पास M state है, so in any other L1 S is not possible. So if a request will come, then request will be getX only. Upgrade नहीं आ सकता. So I think this is again not possible here. If it is in M state in L2, then there will be no upgrade request. Putx request, yes, putx request can come, right? If so, putx from same L1 can come, right? So if it is a M state, then putx request can come. I think, oh, I did a mistake. I think S में putx नहीं आएगा, right? So when I was explaining this, actually I explained M putx. अगर S यहाँ पे S state है, यहाँ पे S है, so there is no chance that upper level पे वो M पे होगा कहीं पे. So if the current state here is S, so ये putx request, this is not possible actually. I missed it. If I think you can, when the lecture is recording, right? So when you visit the lecture again, you just remember that whatever I explained here, actually I explained this point there. M state में होगा तो ही तो आएगा, right? If it is an S state, then there will be no putx request. So I think the first part, I think I have I have explained here. If you have any doubt, you can ask, because the next is replace. So I think I'll not. If you have no doubt, then I'll go to replace. Every point is clear. Oh, I think I should not have it so early. So since it is a recorded video, if you have any problem after watching it again, then let me know. In next lecture, I'll explain it. So since I have 5 more minutes, so I'll quickly explain you the next three. I think it was here only. अगर आपके पास ये वाला है, replace means this is purely for L2. Assume that this set is full. This particular set, as I said, there are many sets in L2, but I'm considering only one set. The set is full and you want to replace a block. Suppose you want to replace A. Current state of this A is S. Okay, then also there are two possibilities. A can be a dirty block or A can be a clean block. Agar if A is clean, then we'll go for replace clean. So ये वाला event call होगा. If S is, suppose the current state is S, so it's a replace clean call होगा. So you know what is if it is a replace clean, then simply we can remove it from A. We cannot it is not required that the data should be written back in main memory, because it's a but if this block is dirty, then we'll call this S and replace. So in S and replace, we have to write this data back to main memory, and then only, okay, I think नहीं कुछ और points है, इतना आसान नहीं है. I'm making it very simple. This can be also a sin, right? ये भी तो हो सकता है. A is in upper level also and A is in lower level also. And now you somehow the replacement policy of L2 is selecting A to replace. A is not dirty, suppose A is clean. But even after clean, you cannot remove directly A, right? Before that, you have to send an invalidation to L1, and that L1 copy will be invalidated, and then you will get an acknowledgement. After getting acknowledgement, only you can only delete A, remove A from here. Though it is a clean replacement, and you have to do this. But if there is no sharer, so वो आपको यहाँ से पता चलेगा ना, यहाँ पे 1 या 2 लिखा रहेगा. If there is nothing written here, it is no sharer, then it is a silent replace. If it is a sharer here, then you have to invalidate that one first, and then only you can replace it. So it means that when we'll discuss advanced level concept, you'll understand that if the replacement policy of L2 is not strong enough, okay, and if someone is attacking the replacement policy of L2, then the upper level cache will face a lot of invalidation, isn't it? It may be possible that A is a very important block in L1, but somehow if someone is attacking L2 or it is convincing L2, then now you have to evict A. So evict A means this upper level cache will face invalidation for this block, right? So you have to understand, maybe when you will read some paper, you'll see this type of lines that upper level caches are getting invalidation because of lower level cache. This is the situation here. If somehow you can this L2 is choosing A as victim, then upper level cache will face invalidation. Here there are only 2 levels. Sometimes there may be 3 levels of cache also. Now if the block is dirty, then I think you have to write it back in main memory. And if the block is dirty, then in that case also both things are possible. It may be possible here that this is AS here, a copy is here AS, and this block is dirty. This situation is still possible. Okay, so I'm not explaining it here. If you remember, during this lecture one, I designed A like this. एक time पे मैंने A ऐसे बनाया था, right? If you check that point, you'll understand. If you watch that point again, you'll understand that how if a block here in last level cache is dirty as well as is copied in others. वो कैसे हो सकता है? Maybe I'll recreate the scene here. First, suppose यहाँ पे AM था और यहाँ पे AM था. उसके बाद ये यहाँ पे putex हो गया है. तो इसके बाद क्या हुआ? ये एस स्टेट में चला गया एंड at the same time this A is now dirty also, right? After some time, if this core is again requesting it in get mode, so ye state very much possible, right? So this state is very much possible. So in this stage, now if you want to remove L2 from L1 from here, means remove A from L2, so this event will call, right? This is the transition that will call. So now here first you have to invalidate the block, वो तो invalidate करना ही पड़ेगा. After invalidating, then also you have to write it back. Invalid to ho gaya, then you will write it back to main memory, and from you have to wait for acknowledgement from main memory also. It is written back in main memory, and when you will receive the acknowledgement from main memory, then only you can say that no, write back is done. Then only you can remove it from this cache. So all these processes are there. So I'll not discuss this next two I'll discuss in next class. But I'll stop here with one important point here, that see, if you want to replace something from here, suppose there is a block A, you want to replace, maybe you need to go here invalid, maybe you have to go to main memory and once you are waiting for acknowledgement, so it is taking long time. Just understand, imagine if you are going to main memory, writing it back, so it's a very long time, right? So, and why we replace a block? We replace a block to make a space for a new incoming block, right? So it means that the new incoming block has to wait, because you are sending a request to main memory. जब तक वो process होके आएगा, then only you will ensure that okay, replacement is done, and then only you can, if you vacate this place, then it is a long waiting time. So what normally does, immediately when a victim block is selected, right, we move it to a new buffer that is called write buffer. Block will be moved here, and this cache space will be immediately empty for new block. And now from write buffer in background, all this that logic that I said, that will be happen in background. So this is called, normally we call as write buffer or MSHR. So this lecture is not, and here this is the completely, we are in middle, but I am stopping it here. Please watch up to this point, and next week we'll continue from this point again. Okay, so if you have any doubt, you can ask me now. I'm stopping the recording here.